today is going to test the limits of the capabilities of both, I guess, lecturers and audience. So we'll have the rest of the day to himself, and we're looking forward to learn a lot about mathematical questions.
Okay, thanks. So yesterday we looked into things, so we defined Feynman integrals, which are the things we want to study, and we defined periods, and we said that, well, in dimensionalization, Feynman integrals are periods. And then we discussed IDPs, integration by parts. We said that, well, in dimensionalization, total derivatives vanish. And from this we get essentially linear recursions in the exponents of the propagators. And we look at the example of the two-point function one loop with master's propagators. It was this lattice, and then we had recursion relations in n1 and n2, which are the exponents of the two propagators. And we said, okay, well, even though we have an infinite family of integrals that we would want to compute, in the end, only it would be one because all the others are proportional to one corner integral and one one. Okay, do you remember that? Are there any questions about that? Yes?
What was the motivation to have, I mean, the n and those two n's?
Yeah.
For the two-point function?
Yeah.
That doesn't represent anything that's, like, it's real brain, it's not more than one.
That is incorrect. You see, you can chain many of these things together, and that will always be the same propagator. So that is the same as that thing to some power and some bubble. So you see that you get propagators to higher powers naturally. That is the first thing. They are physical. They show up in computations. It's not that you say, I only want power of one. That's all I need. These things with higher powers to show up. The second, yeah.
But these diagrams are moving diagrams, right?
Yeah.
So it can't show up on like one loop level.
At one loop level, no, because then you just have simple propagators. If you draw the Feynman graphs, they will come with simple positive propagators. But the other reason to consider these things is much more basic, which is that it gives you a handle to find the minimal derivatives that you can compute. And these are recursion relations. If you solve them, you get the basis of integrals that you can compute, independently of whatever the exponents are. That is a nice thing. It tells you that that is the minimal set of inputs to compute, and usually integrals that have fewer propagators are easier to compute. So as soon as you realize that you can write an integral with 5 propagators for an integral, a linear combination of integrals with 4, 3, and 2 propagators, you're happy. And that's what can come out of these recursions as well. More questions? No. So, as we said it just now, by solving these recursions, you get a basis of integrals for a given family. The family is this, what they call family here is like this function of the exponents on this lattice. Often in literature, such a family is called a topology because you can represent it by graphs essentially. The members of this basis is what is often in physics literature referred to as master integrals. when you hear people talk about master integrals, it means that they're just talking about the basis for a given family of integrals. Note that just like any concept of basis, there's some arbitrariness in there. Sometimes you hear people say, this is a master integral, this other thing is not. That per se is an empty statement. The only thing that makes sense is to say, I fix the basis, and then I can decide if that element is my basis and the other element is not, so I can write a linear combination of the basis. But there's no such thing as being intrinsically a master integral. Even though you often hear people say such sentences. Now, the last point I want to discuss here is, this is all very nice, but how do you find it? So how do you solve the recursions in practice? And in case of the two-point function yesterday, it was easy, right? We had a recursion in two variables, linear, and you could just solve it by hand and see that how things move in the lattice, and then we end up in the lower left corner, 0.11. Now, in practice, you will have, and things that you consider will be integrals with 10, 12, 15, 17 propagators. And sometimes the dimension of the basis is 100 dimensional, 200 dimensional, 500 dimensional. So that's not something you can easily do by hand. Okay? So you have to come up with clever ideas of how to solve these recursions. But one technique is, of course, solve the recursion exactly if you can. But yeah, if you can't, you have to come up with other ideas. One very famous one, very practical one, is what is called the Laporta algorithm. And it connects to the question I was asked before. Why do you consider these integrals with higher powers of the propagators? They don't show up. Well, they do show up, but then, as your colleague pointed out, well, in one loop, for example, you wouldn't need them. So at a given loop order, you only need a certain subset of these integrals for all practical purposes. So instead of solving the recursions exactly, just sample them. Plug in values for n1, n2, and 3. And what you build is a finite size linear system that you can solve. So plug in values, that's really a sample, but it's not really a random sampling, and then you choose consecutive integers, right? 1, 2, 3, 4, and so on. And this leads to a finite size linear system. Which you can just solve.
So you mean I put an upper bound?
Yeah, you put an upper bound, yeah. Because you know that you will never need the integral where one of the propagators has power 1 million. In your computation, you won't need it. So no need to solve the system in general. It's enough to solve it for small enough values of n1, n2, and 3, and 4. That gives furnishes you finite size system, linear, that you can solve. Okay? At least solve in principle. In principle, because that system will not be, well, the question is, what are the coefficients that appear in there? The coefficients will be rational functions in all the scales of your problem and in the space-time dimension. So this will be a finite system with coefficients that are rational functions. With many variables available. And now, if you ever played with systems where you solve things not with numbers but with functions, you can imagine what happens when you solve linear systems, say with Gauss elimination. You start with something simple, you solve it, you have to divide at some point, you take the thing, you plug it into another rational function, you multiply everything out, so what was a linear polynomial becomes a quadratic polynomial, and you do that 1,000 times, and things get bigger and bigger and bigger, until you won't be able to fit it into the memory of your computer anymore. And that happens very quickly. And so that method was introduced some 20 years ago and was very successful. That's how most of the multi-level computation with few scales were done. But nowadays, if you want to have more scales, or more legs, many legs means more than 4. So you want to do more than two scattering, that is many. Then, that thing is not really working anymore. I mean, not without a lot of effort. So what people are doing nowadays is exploring new things. One of these ideas is, for example, that something that goes in the name of finite field techniques. I'm not going to discuss, I'm just going to say, and it's basically, the idea is, plug in numbers for all your scales, so now you have numbers. The issue is still that these numbers will be very big. So reduce them modulo some prime number. You have modulo 2, modulo 3, modulo 5. And for each of these, you can easily solve the system because the system is very small coefficients. And there's a mathematical theory that allows you to do the following. If you do enough samples, so you now plug in numbers with the scale. If you do that for enough values and for enough reductions modulo p, you can actually reconstruct the exact rational function. So instead of solving a big linear system with rational functions as coefficients, you solve many systems with numbers that are very small because they are reduced modulo prime numbers. Well, small, they get to be large, but they are not horrendously large. And especially don't grow. Grow whenever you do one step in the Gauss algorithm, you see that the integer becomes larger. If you work modulo some prime, you cannot grow because you fix the size. The other thing which people explore nowadays is that people realized that everything is done here is just literally the physicist version of the Ramp homology. But the only thing we've done is we've classified our integrals modulo total derivatives. Right? We've said whenever you have a total derivative, it integrates to 0. So it's equivalent to saying, I look at the integrand and I throw away terms of total derivatives. More precisely, this has connections to twisted version of the Ramp. So the Ramp homology, but with coefficients in some local system. And then what you realize is that this reduction to a basis, I'm just going to use the word, I'm not going to discuss that, corresponds to computing intersection numbers between differential forms. Yeah?
Just say a few words about what the Ramp homology.
The Ramp, so if you don't know what it is, probably even if I say a few words.
I haven't had a lot of differential geometries.
So you know what a differential form is?
Yeah.
So you know that they can differentiate differential forms. So I have a form, I can compute its derivative. You can also go where you know that if you square the differential, you get 0 probably. So now let me look at things that are called co-cycles. So I look at the set of objects such that the omega equals 0. And I work now modulo things that, well, in there I have everything that is itself, every omega that is already a derivative will also lie in here because we squares it into 0. So I can say, okay, let me take out those that are already derivatives themselves. So in other words, if I give you two differential forms, two integrands, I say two integrands are the same if they differ by the derivative. In other words, the integrals will be the same. Okay? And this quotient you call a cohomological. That is the Ramp homological.
So this is like modding out by the surface.
If you want, that's what corresponds to finite, yes. But you see, it's literally what we did. We said that everything that is a surface term is not relative to the full way. So the mathematical setting to study this stuff is common. Now you need something slightly more elaborate, but the basic idea is whatever just said. You want to classify integrants of the total derivative. You are just to say that if you look at the literature, or like that's what people are interested in right now in this context.
So I would think the integrand also like the measure, so I would think that as a differential form.
Yeah.
Okay.
Okay. So that is a way to reduce the number of integrals that you have to compute. To get the basis of integrals that you need to compute. Any questions? Yeah?
I mean, the anthropology is well defined on manifolds, but I mean, the surface we are computing on is.
You don't do it in Dupermental space. You go again to some Feynman parameter space or to even some other representation called Bykov, where you really work with algebraic varieties.
Yeah, but with algebraic varieties and manifolds, right?
Sorry?
With algebraic varieties and manifolds.
As far as I know, at least those that show up here, they are.
Okay.
Unless, I'm not an expert in algebraic geometry, but at least my algebraic varieties, they all come equipped with topology and they all have the round homology groups. More questions?
Are there any results or practical software based on this idea?
Sorry?
Is there any practical software or some kind of results which have been obtained with this idea?
Results? I would say everything in modern computation was ever done uses that.
Yeah, but new results.
Sorry?
New results.
New results? What do you mean by new results?
Well, usually when you introduce a new technique, you want to compute something which has not been computed before. This is right.
You mean for these things now? Or are the pieces in general? Or these? For that?
Yeah.
No, people are just exploring it.
Okay.
People are just exploring it as a possibility to get rid of the restrictions of the Laporte algorithms. Finite techniques were used for 5-point computation, two loops. That stuff was only introduced like a year ago, so it's not at the level that you can mass produce it. But that should not prevent people from exploring it as a route to go if you know that the other route is blocked. More questions? So then we turn now to the question of what do you actually get when you evaluate the integrals. So from now on, you only need to evaluate our master integrals. We assume that we've gotten them. So what comes out of computing the master integrals? So yesterday we said that the kind of numbers that you get, the kind of functions you get, rather special. They are periods, integrals of rational functions. Now, periods still form very large space. there's still many things in there. And so, well, we'll focus on the subclass. But to understand it, let's make a first look at an example. So let's look at this integral. So that's the integral I may want to compute. And I will just tell you what the result is, and then we can discuss it. So I do the computation in b equals 4 minus 2 epsilon dimensions. It turns out that this integral is finite in 4 dimensions, so they are not poles. And the first term in the Laurent expansion epsilon so this just indicates terms in the whole expansion left over. So that's what I get. Where the variables are as follows. Yes?
What is this z and d?
As the variables are as follows, and I write it now. So they are defined in this way. You can invert it.
Where B is the second ratio of
Yeah, sorry.
yes, and it's evident, but its external legs are massive. They don't square to zero.
Yeah, unless I say anything else, they're massive, yes. Okay? So, that is probably the simplest integral that is not completely trivial. Completely trivial in the sense that the 1 to 2 point function is trivial in the sense that it just logs. That is the next one. And already there you see it gets pretty complicated. So you have complicated functions, so you get a log. I'm not sure if it's complicated.
What is B?
Yeah, I will explain it now. So you have these functions. You have the log, which, depending on your taste, you can call it an easy function or complicated function. So the log, I guess you all know. I can define it like this. Li2, that's called the Dye logarithm. It's defined in the following way. Now it's an integral of a log multiplied by 1 over t. That guy is a new transcendental function. You cannot evaluate it in terms of any other function that you would prefer. You have to live with it. And then you also see that the arguments of these functions are, in general, very complicated algebraic functions. Okay. So if we try to make an inventory of what we get when we do loop computations, so we do get algebraic functions. So like 1 over z minus z bar, which if you do the computation is just the square root that you have in the definition of z bar. You get logs. You get these E2s, they are called in general Polylogarithms. And no surprise, I can define them for every n. And this function, I'll just give you a definition and then we can discuss it. This function has maybe a matter definition that you're more familiar with it is this. It's a series representation in some region of its range. All these functions are multi-valued functions. Now, of course, I may also get other things. For example, if I have Ln, I may have Ln evaluated as a constant argument. That is, well, if you take a series representation, and this I guess you recognize. It's just the Riemann zeta function evaluated at some integer argument. So those are the things that you get when you do the computations, typically. Now, if you do one loop computations, it turns out that this is indeed all you get in 4 dimensions. In 4 dimensions, every one loop integral can be written in terms of logs and dilogs. And I say in 4 dimensions, you can ask what do you mean by that with integral divergence. I mean up to terms that are order epsilon. So if you take a divergent integral, it may have poles, it has a constant term, then I throw away the rest. Up to the constant term, I will only find logs and dilogs. Okay? So that's quite nice. So I think, okay, well that's beautiful. So there's kind of a natural bound on the kind of functions that I can get. It's complicated, yes, but okay, there's one new object I need to understand, this is V2. Then you go to 2 loops, and all hell breaks loose.
Maybe some type of observational theorem that like to 2 loops up to this number of layers, this is the work that can happen to you?
No. It's really all hell breaks loose. Even the 2-point function, so which is the simplest guide you can have, you find modular forms and elliptic polylogs. For many legs, you find things that are, well, we know it's, the geometry is a surface of genus 3, but we have no clue what it is. If you go to 3 loops, I think there you get a K3 surface. If you go to for loops, we know examples where we get Calabi-Yau manifolds. But already at two loops, already in the 2-point function, you get two elliptic curves into modular forms.
But for fixed loops,
no one knows what comes out. There are certain things which you can kind of exclude, but I don't know of any like theorem or statement that says the upper bound for two loops in 2 dimensions is. I mean, you know that the weight conjectures and so on, but those are first of all very specific to certain subclasses and so on. But in general, I wouldn't know what the bound is like at 2 loops. More questions? Before we open Pandora's box. No? Okay. So I guess in general, if you have to extrapolate from here, what you could get, the most natural generalization that you get is what is called, so these are polylogs. You have now multiple polylogs. So those are defined as follows. So let's motivate it. So you see here I have this recursive definition. We can also discuss maybe later why these things look the way they are. But you have here a recursive definition where you integrate in more and more 1/t's. You see the pole is always at 0. So if I want to include more variables, the natural thing to do is to change the location of the pole. Okay? So that is the first generalization that you can naturally imagine, is that you say, well, I continue my recursive definition, but I allow to shift the location of the pole. Okay? Now, if you are attentive, you realize that this only holds, well, you need, if an is 0, there's a problem because you have an endpoint singularity. Now, you're going to do it the pedestrian way and say, when all the indices are 0, then it is just an open. With that, the class of functions is well defined. Why that is a good way to define it is a different story. It's mathematically much deeper, but functions per se are defined. Okay? So I guess you see that that is really the natural generalization of this integral to many variables. Now these g's, they also can be written as a sum similar to the sum representation that we have for the other one, but we're not going to discuss it due to lack of time. But so the first topic that we will discuss in detail is what are these functions? What are these polylogs? I will often say polylogs, but I always mean multiple polylogs. Okay? Because that is kind of the simplest class of functions that you can encounter if you do higher level computations. Note that it doesn't stop there. It's already all hell breaks loose. Already, as one side comment, if I have time at the very end of the lectures, I'll make comment more on that. Already that guy with massive propagators, that guy needs generalizations of NPL stands for multiple polynomial. Already that simple integral needs generalizations of these class of functions to elliptic curves, and also this closely related to things like Eisenstein series, if you know what they are. If you don't know what they are, it's the material, that's what we're saying. Maybe words here. That is really just like the simplest thing you can have. But it's already very rich, as you will see. But keep in mind that starting from two loops, already very early on, you get much more complicated things. What saves people who do higher loop computations with the AUC is that these new things usually show up in two loops and you have massive propagators. Usually. Also, if you go to enough lengths, they also show up for massless propagators, but say for 2-to-2 processes, these show up for massive propagators. And then the AUC averages are so high that you don't care about internal masses for many cases, not for all cases. So as long as you don't have things like top quarks or electroweak bosons, you forget the masses, and then you get away usually at 2 loops or 2-to-2 scattering with these functions. As soon as you have top quarks or electroweak bosons, then you do hit this already for 2-to-2 scattering. Okay. So, what are some properties? So, the first thing you can notice, if you look back at our example, is that, well, it contains logs and dilogues, and there are, well, transcendental functions. Transcendental meaning they're not algebraic functions. You cannot write them in terms of algebraic functions. Though that is technically conjectural statement, that is not proven mathematically. No mathematician can even doubt the statement, but it's not technically proven. Now, the other important thing about these guys is they all have discontinuities. And that is a general feature of all of these loop computations. Why must that be? Why do I know I must get functions that have discontinuities? Why can it not just be a simple algebraic function? For me, discontinuity means not the square root discontinuity. Really like...
You mean physically?
Physically, yeah.
Because of particle threshold for the
yes,
particle.
because of unitarity at the end of the day. Unitarity tells you that your amplitudes have discontinuities. Okay, so just based on that, you know you must get complicated functions. You cannot get away with algebraic functions. And maybe it's good to spend a bit of time discussing what discontinuities are, because often the way this is taught, say, in undergrad courses, is not the way that is best to understand what's going on with these functions. So, I guess you all know that, so that's a formula that you've probably seen. The discontinuity of the log is 2 pi I. Right? That's probably something you've seen. Now, how would you interpret that? What is the meaning of that sentence? The way you should think about it, but I'm going to say that sounds very trivial and just looks like just reformulating what you know, but it's important if you want to understand what's going on for the general case. My log, I had defined it, but it's It's no longer there, so let's write it. And I defined it like this. Right? That was the definition of log. So what does that mean? That means I have an integral that starts from the point 1 when I integrate to the point z in the complex plane, and the integrand has a pole at 0. Right? That's the geometrical picture of corresponds to this integral. I integrate from 0 to 1, something that has a pole at 0. Now, I guess you all know that, okay, I drew here this line segment 0, 1. That's kind of what we implicitly understand by writing integral from 1 to z. But I guess you all know that Cauchy's theorem tells me that that integral is the same as the integral of this path. Right? So, that means I can choose any path I like. Except that whenever my path encircles 0, then I get the contribution from the residue. Right? If I choose this path here, then I do not get back log z, but I get back the contribution from this circle, which is a residue, which is 2 pi I, plus log. So the way you should think about discontinuities is really changing the path of integration. Now, in undergrad lectures, you usually told, the log has a branch cut that goes from 0 to minus infinity, when you cross the path, the function jumps by 2 pi I. Right? You have to be very careful with these pictures. That is correct, there's nothing wrong with it, but there's nothing intrinsic about saying this branch cut is along the negative real axis. You could just as well have it point like this, or even here. There's nothing wrong with it. This idea of a branch cut is simply that I say I make a whole tour around it, so I necessarily cross that line. The reason why it is done that way conventionally is that from the definition that I gave, I integrate along a straight line path from 1 to z means that that is a well-defined statement. You see, for every point in the complex plane, I can draw this straight line, except for the points that lie here. Because there I cannot, because my path was in 0, my straight line path. So that is where I see where the branch cut comes from in this picture. And it really means you have a pole somewhere, you have an integration path somewhere. You can deform the path in any way I like, as long as you don't cross the singularity. If you cross the singularity, then you pick up a residue which is proportional to 2 pi I. I insist on that because if you go to these guys, you see you have poles in many places, in many integrals. Thinking in terms of branch cuts that go from some point to infinity can be a pain. This is much easier than to visualize it as what is a path of integration and do they differ by some residue at some point. Okay? So another property is that these functions satisfy many relations. I give you some of them. The simplest one is the following. can even do this one as an exercise. It's very easy. You can state all the arguments, as long as there's no 0 at the end. You can try to prove there's an exercise, it's very easy. Just change the variable. Another identity which is already less obvious, still easy to prove if you are motivated. Imagine an evaluated function at 1. You know that evaluating at 1 is not such a weird thing to do, because since I can scale in any way I like, I can put k equals to 1 over z, and then I get 1 at the end. It's not identity. There's another one. Well, if you go to Wikipedia, let me write it for Li2. Maybe I should just say that. So, if it's not obvious, these Li-ends are just in here, okay? So Li2 of z is minus G0, 1 of z log 1 minus z over a. It's G a z, provided of course that a is not 0. If a is 0, in this case, E3 of z is minus G 0, 0, 1 z, and I guess you can imagine how this goes on. So all your Li-ends are just subclasses. There are many more relations. For example, there is a relation. I'll write it down with U2 because it's easier to write. Well, then I remember it. That's not a relation. And you can go on like this to eternity. There are many relations. So what we'll see this afternoon is, what is the structure behind these relations? How can you understand them mathematically? It's very important for computations, because when you do practical computations, you usually run into the issue that you have to deal with certain entities. Imagine, go back to high school where you had sines and cosines. Okay, and you had all these tables with sines and identities for sines and cosines. I guess you remember that solving problem classes in trigonometry was a pain because you had all these identities among sines and cosines. Here it's going to be the same, except that you don't know the identities. Okay? Still, it turns out that this problem is easier. To some extent, okay? Okay, so I think this is a natural place to take a break, and if you have questions. Yeah? Sorry, can you speak up?
I wonder whether this that single value would display be the same as the logarithm.
What do you mean as single valued?
Well, the logarithm, like you said, I need to have a limiting number of sheets.
Yes.
Is the same space the space where these functions are defined, or is it something else?
I'm not understand. So what do you mean by if you consider this function as single valued? I'm not sure I understand.
Well, by the definition, there is this integral, right?
Yeah.
As you mentioned,
Yeah.
it depends on
The path, yeah.
on the path. And then these paths are
Yeah.
like
Yeah.
sheets.
Mm-hmm.
And is, my question is that, so I can consider logarithm as a single value function, right, if I have an infinite number of sheets.
Yes.
And is the same true for these, and is it the same space?
Ah, okay, I see now what you mean. Well, okay. So, let me first try to rephrase the question, make sure I understood the question correctly. So you're saying the log, we usually think about it as a multi-valued function, but equivalently I could also say it is, well, I have my complex plane, and I take out the cut, open it up, and then I look at it as kind of a spiral. And indeed, you're right, on that space, which is the covering space, it is a single value function. There's, of course, a natural projection for my spiral down to my base, which is circle. That's just looking at it like this. Say, I just take a circle, in the covering space it would look like a helix. And then the multi-valuedness comes from the fact that points here differ by 2 pi i's. And that is what I see here as going around the circle and picking up 2 pi i's as I go along. Right? Now, if you go to multiple polylogs, the story is in principle the same. Except that now I have many variables. So first of all, I'm in multidimensional space, and I would have many cuts. So even if you have just one variable, but you have, say, the a's are constants, this would be a1, a2, a3. Yes, I can consider the covering space, but I wouldn't know how to visualize it. But the story mathematically is exactly the same. That's why in that case, I think it's, for me at least, it's easier to think about the path, because then I see what happens. But mathematically, you're right. I mean, I can go to the covering space, and on the covering space, it was a single value function, and my covering space would get it by gluing together the different sheets. But doing that, if you have many cuts, is a pain. Now you would have not just, now you would have to imagine also the a's could be variables themselves. They could move as well in some other space. Now the a's may even be functions of z. So the a's would move in some other space, however coupled in a way, and so it gets horribly complicated too, if you really want to visualize it. But mathematically it's exactly the same story. More questions? Yeah.
Now, the last relation of this, we like to follow some integration by parts on
Yes.
the single logarithm. Are there similar relations to the higher polylogarithms?
That's what we're going to see this afternoon.
Okay.
You're correct. So I can, of course, and so what you said is essentially this. I can prove it by taking the integral representation in the sum. That's correct, and of course, that must be the case, because then the integral defines the function, and all the information sits in that integral. I must be able to dig it out from there. The question is, if I give you now 2,000 of these g's in 5 variables, and you want to figure out, can I find precisely the right set of relations to boil it down to, say, a single line? Then, yes, of course you can do it with integral representation. There's nothing wrong with that. But it becomes really a hard exercise. But we'll see this afternoon that this idea of this integration by parts is encoded in the combinatorial structure. There's some algebraic structure behind which does kind of the combinatorial thinking for you. But the basic idea is different what you said. I mean, it's the integral of the function defined by an integral, and all the information is in that integral somewhere. More questions? Nope. So much time.
I would
So you still alive? Oh. Okay. And there's one more topic we can cover before lunch, before going to the real algebraic stuff this afternoon.
Is there a natural inverse function of the polylog and the multiple polylog? In the sense that the exponential is the inverse of the polylog?
I don't know. I don't know, simply because those are not the kind of things that I would be interested in the following sense. We said yesterday that Feynman integrals give you periods. The logarithm is a period. The exponential function is not. So maybe there is such an inverse, but it would not be any of the functions that we would call a period, and it would show up in this context. Yes?
Something you mentioned yesterday, the scaleless integral bound.
Sorry?
Scaleless integral bound.
Yeah. Okay. So, yes, so yesterday we said in dimensional realization, scaleless integrals vanish. So, before we do that, we do something else which is totally obvious. I give you my integral, and let's say it depends on my scales, which I call S1 to Sn. Can be masses, can be dot products, can be whatever you have. But I can also assume that they are independent. Okay. Now, I guess you can easily convince yourself that just by dimensional analysis, you know that I can pick any of these scales. And so there's some number alpha, which is the dimension of the integral, times some integral, which now is dimensionless and would only depend on the ratios of scales. Okay? I think that is not too hard to see. The other thing which we can now ask, okay, what is actually alpha? Well, if you remember how the integral was defined, and then I had, say, propagators. Let me not consider for now the numerator polynomial. Wouldn't change the argument anymore. So what is the dimension? The dimension is, if you want, so this is actually a priori a function of my momentum, right? The external momentum. And it's long as invariant, so I know it can only depend on velocities. And also on masses. So the dimension is defined literally as, well, let's also write the masses just to be consistent. M1 to mk. So the dimension is defined as follows. Take all your momenta and rescale them. Take all your masses and rescale them. Actually, the purest is actually a function of m squared. Now, I think it's easy to see that if you plug that in here and you rescale the case accordingly, what you will get is essentially some lambda. It's homogeneous in lambda, that's the important thing. And it will come with minus 2 and 1 minus 2 and k. Right? Every propagator scale is like lambda squared in the denominator. And then the measure scales like L times D. Right? And that's okay, so what you see is that your alpha will always be L times D, and be careful, there's 1/2 here because S has dimension value squared, while it's for find lambdas the energy dimension, and plus some integer. divided by 2. Right? That's the most unknown thing I can possibly imagine. And so, that is actually minus L times epsilon. So D is some integer minus 2 epsilon plus some integer. And so you see that at L loops, the dimension, so your integral will always have a piece that scales as some scale, and only some scale minus the power L times epsilon, times a function times, well, plus some integer, right? Which I may not know what it is. It may even be 0. Times a function which is dimensionless. Okay? Now, from this, it follows that scalars integrals vanish in dimensionalization. The argument is the following. If you have, so you know that by dimensional analysis, your integral must be some scale raised to the power epsilon. But if you have no scale, the only thing it can possibly be is that f is 0. Otherwise, dimensional analysis wouldn't work. You can also see it as, okay, imagine you have a scalars integral, put a scale, put a mass in some propagator. You have one scale, you know that that thing must be that mass raised to the power epsilon times a constant. Because you had only one scale. And now take the mass to 0 at the very end, before you expand in epsilon.
You know, just like epsilon.
Yeah, you say you put yourself in the, it defines everywhere for epsilon, at least to analytical equation. So put yourself somewhere where, say, epsilon is negative, so you get 0 to some positive power. In that region, it's 0, so analytical coordination will be 0 everywhere. Okay? So it's really a statement about dimensional analysis. The fact that you know that, well, if you're more mathematically inclined, you would say that it comes from the fact that there's a natural action of some group which rescales the whole thing. If you're physicist minded dimensional analysis and you know that there's no scale, the thing must vanish because otherwise it must have a dimension. So it's either 0 or it has dimension. Yes?
So why can we assume here that the numerator, that we don't have a polynomial, that would also...
It wouldn't change it, because if I have a polynomial, here, that thing would just change this thing by another integer, which is the dimension of that thing, the numerator. I can also assume that that guy has a homogeneous energy dimension itself. If not, I can break it into polynomial, I can break it into sum of pieces, which have a definite energy dimension. And also in practice, you can only ever have homogeneous polynomials in dimension, right? So that would only shift by an integer. But you see, the integer that I put here doesn't play any role. It's only about the fact that in Limerick I have this epsilon sitting there, that there's a non-integer energy dimension in Limerick. That is what it would say. Because otherwise I couldn't conclude. Otherwise, n tilde may as well be 0, and the integral would have no dimension at all if that guy wasn't there. It's really that in Limerick, the energy dimension is non-integer.
Sorry, so you said that if epsilon is an integer, I could tune epsilon to cancel n tilde?
No, epsilon is not an integer. Epsilon is
if there is no Limerick, and I think just epsilon.
If epsilon is 0, which is like that, then you have integrals which have just 0 energy dimension. There's nothing wrong with that. Right? It would just be something like, take an easy example. D equals 4, and you have a 2-point function, so you have two propagators which have dimension 2 each. The measure in 4 dimensions is dimension 4. The 2-point function, one loop in 4 dimensions, if it was convergent, which it isn't, would have dimension 0. Okay?
If I have an arbitrary thing, I can tune the dimension
to get something massless, for example?
If you have an arbitrary thing, no, you never, the dimension is fixed, you cannot do it, right? The dimension is given. Your statement is that you know that there must be some scale raised to the power epsilon if you work with the bracket. The energy dimension is not non-integer. So there must be some scale raised to that power in your answer. So if you have no scale, well, the only thing that you can have is that the ash that multiplied is 0.
You could argue that they infinity.
Yes, but as I said, you know there's at least one region in where epsilon, where the thing is actually 0. More questions? Okay, so then let me now do the following. Let me define A as, and put it in quotation marks, I define this to vector space spanned by all functions. I will not be more precise than that. I think intuitively it's clear what that thing is. It's just whenever something is a polylog or product of polylog or linear combination of polylogs, at whatever arguments, constant arguments, whatever arguments, I dump it in there. Okay, it's something that is visualistic, the definition is visualistic. I think intuitively it's clear what this thing means. Okay? And let me define something else. So we have polylogs were defined by an integral. Okay, erased definition, let me quickly write again. So that function say has weight n. It's a number of integrals, let's see. Okay. And also say that the weight is additive. So what I mean by that is that the weight of A times B is the weight of A plus the weight of B. Functions of weight 0 are algebraic functions. Logarithms have weight 1. Dilogarithms have weight 2. And so on. So weight 0 would be algebraic functions. Weight 1 would be the logarithm. Or pi, because pi is essentially the logarithm of -1. Let's not discuss it, it's plus or minus that pi, but it's log of -1. Weight 2 would be things like log squared, z, or log x times log y, or dilog z, or pi squared. or pi squared over 6, which is a linear combination of pi squared. Okay? Any linear combinations are fine, because we're talking about vector space. Weight 3, I would have all possible guys. I would also have things like zeta 3, which is lead 3 of 1. And so let me write A as n, where AN is the Q vector space of all FPLs of weight n. Just jam them all together. Okay, I think that's obvious that I can do that. And so this is no, I think this is already coming to the end. I think this is a natural place to stop. So this afternoon we'll start from there, and we'll see that there's actually much more structure in this A. In particular, we'll replace this union by a direct sum, which is a highly non-trivial statement. It sounds trivial the way it is written here. It's highly, highly non-trivial. We'll also show that there's a natural algebra structure on A, and even a co-algebra structure on A. But I think this is a natural place to stop. So unless it's questions, I can break here for lunch. Yes?
The definition of algebraic, this is a definition, additivity?
At this point, yes. At this point is defined that, well, whenever you give a polylog, the number of integral signs is defined as the weight. And if I have a product of polylogs, I define the weight of the product as the sum of the weights.
And is it clear that this is well defined?
That is one of the things that we have to see, yes. Actually, that is why I wrote there union. If you want, as a filtration, if I would say it's up to weight n, then it's clearly well defined. The non-trivial part is it's really well defined as the weight is preserved.
Questions? Not the case. Let's have a lunch break until 2 o'clock. So we're back here at 2 o'clock according to schedule. Well, yeah, have a good break. And let's thank Claude again.